Today I'm going to talk about how to find the magnitude, in this case of h of t, and the step response using h of t and x of t using Fourier transforms. H of t in this case is 1/2 times the quantity e raised to the negative 3t plus e raised to the negative t times u of t, and x equals u of t. To find the magnitude of h of t, the best way to go about it is to find h of j omega, or h of t in the frequency domain. To do that, we use e raised to the negative at u of t transformed into 1 over j omega plus at. Therefore, the Fourier transform of h of t becomes 1/2 times 1 over j omega plus 3 plus 1 over j omega plus 1, which turns into j omega plus 2 divided by the quantity j omega plus 3 times the quantity j omega plus 1. Using the value of h of j omega that we calculated on the previous slide, the magnitude of h of j omega then becomes the square root of omega squared plus 4 over the square root of omega squared plus 9 times the square root of omega squared plus 1. And also for reference, the angle of h of j omega becomes arctangent of omega over 2 plus arctangent of negative omega over 3 plus arctangent of negative omega over 1. To find y of t, or the step response, the easiest way is to find y of j omega, which equals h of j omega, which was solved on the previous slide, times x of j omega, which, as you know from the beginning, x of t equals u of t, and the Fourier transform of u of t is 1 over j omega plus pi times delta of omega. Therefore, y of j omega equals j omega plus 2 over the quantity j omega plus 3 times the quantity j omega plus 1. All of that is multiplied by 1 over j omega plus pi times delta of omega. Simplifying y of j omega from the last slide, we get j omega plus 2 over the quantity j omega plus 3 times j omega plus 1 plus 2/3 pi of delta omega. The reason for the 2/3 is because if you plug in where the delta function is defined, which is at 0, you get 2 over 3 times 1, which is 2/3. To solve the first part of y of j omega, the easiest way is to use partial fraction decomposition, which, as you can see, has been solved completely, and the result is 2 over 3 divided by j omega plus negative 1 over 6 divided by j omega plus 3 plus negative 1 over 2 divided by j omega plus 1. Taking y of j omega that we got on the previous slide, we can then see that if you take this last term, it becomes 2 divided by 3 times 1 over j omega plus pi delta of omega, which, as you saw on the previous slide, the note, and also at the very beginning, we saw that u of t Fourier transforms into 1 over j omega plus pi delta of omega. Therefore, when we get y of t, we get that the beginning becomes minus 1/6 e to the negative 3t minus 1/2 e to the minus t, and that's multiplied by u of t, plus 2/3 u of t.